Okay, we're going to start talking about motion in a plane now, chapter 3. So, in chapter 2, we talked about motion in one direction. We call that kinematics. We were focused just on the motion of of a certain object or particle that is moving in one dimension. We weren't concerned with what was causing the motion. We weren't concerned with the dynamics. We're not going to concern ourselves with the dynamics here either. We're just going to talk about the motion and the equations of motion in a plane, so in two dimensions, an x direction as well as a y direction. We won't worry about three-dimensional motion in this course. So the goals for this chapter are to study position, velocity, and acceleration, just like we did in chapter 2, but this time we're going to talk about it in terms of vectors. So we'll talk about it in terms of things that have both magnitude as well as a direction. That's what a vector is. We're also going to frame or set up two-dimensional motion, some problems, as it occurs in the motion of projectiles, or we'll call this projectile motion. There will be several assumptions that we'll need to make in order to have kind of neat little projectile motion problems, and those assumptions are going to be very important to understand when to use them and how to use them. We'll also sort of confine our talk of two-dimensional motion to being strictly in a circular path. So we'll call this uniform circular motion. We'll define this in this chapter. And basically it's motion that moves in a circle continuously at constant speed. The coverage for the chapter will be sections 3.1 through 3.4. So velocity in a plane, two-dimensional velocity, is developed pretty much the exact same way that we developed velocity and acceleration in chapter 2 when we were talking about it and it being a straight line. The only difference here is that now we can have movement in two dimensions. So we can have both an x direction as well as a y direction. So we need to talk about the change in the position vector. Instead of just being a change in the position, we need to talk about a change in the position vector. So what do we mean vector, which is denoted by r, like you saw in the previous slide there. So when we're defining the velocities and the accelerations in two dimensions, we have to use the position vector. So what is the position vector? Well, it's exactly that. It is a vector which gives us the position of a certain point. So say we have a coordinate system where we have our y here and we have our x over here. And we have a couple points. We have point 1 is located right here and point 2 is located right here. The position vector would be the vector from the origin right here up to the point. So up to point 1, this would be the position vector 1, or we'll call this R1. Similarly, we'll have position vector R2 would be the vector from the origin up to point 2, and we'll call that position vector 2, or R2. The arrow on top denotes it as a vector, right? So when we define the average velocity in two dimensions in a plane, we define it as the v average velocity, is the change in the position vector. So that's vector R2 minus vector R1 divided by the time it takes to get there, or the time it takes to change. So T2 minus T1. That is the average velocity in a plane. Now, subtracting vectors is just like adding a negative vector, right? So R2 minus R1 is the same thing as R2 plus a negative R1. So if we were to draw a negative R1, and we'll draw negative R1 at the head of R2, then we'll get this. So this is vector negative R1 right here. It has the same magnitude as vector R1, but it is 180 degrees off from it. It's in the complete opposite direction. So this is vector negative R1. So now we can have vector r2 plus negative r1 is the same as r2 minus r1. And when we're graphically adding vectors, we use the tail to head method. So we'll draw a line from the tail of R2, which is the starting point right here, and then the head is where the arrow is. So we'll draw it from the tail of the first one to the head of the second one. So doing that, we have our average velocity vector from here to here. And this is the average velocity between when it goes from point 1 to point 2. Which you can see that if I were to move this up here and put it from the head of P1 to the head of P2, or the head of R1, excuse me, the head of position vector 1 to the head of position vector 2, you see that it goes from head to head, and it's the same exact average velocity vector. So that's how we get average velocity in two dimensions in a plane. It's simply the difference of the position vectors divided by the time it takes. So since we're talking about motion in a plane, we can now actually talk about the accelerations and velocities in terms of a displacement as well as an angle. So we can talk about the x and y coordinates of we have here a velocity vector. So the x and y coordinates of a velocity vector in terms of displacement as well as an angle. So we have our velocity vector here, and we have some angle here, right? This is the path. This blue line is the path that the object follows. So I'm going to talk about instantaneous velocity because it's defined the same way as the instantaneous velocity when we're talking about in a straight line. So I'll jump into that here. So the velocity vector, if I were to take this point right here and find the instantaneous velocity, then it would be a vector that is parallel to the, or it's not parallel, I'm sorry, it's tangent to the path at that point. So this line right here is tangent to the path the object takes at that point. And that's the instantaneous velocity. It says instantaneous velocity vector is always tangent to the xy path at whatever point we're analyzing it. We have the velocity, a couple of definitions over here. The velocity, instantaneous velocity is defined exactly the same way that we defined it in one dimension. It's simply the limit of the change in the position vector divided by the time as the time it takes, delta t, goes to 0. So it's the same definition. We're just getting smaller and smaller time intervals. The magnitude, this right here, this absolute value symbol is the magnitude. So this is the magnitude of the velocity or the speed. Magnitude of velocity is the speed. And that's equal to the square of the x component as well as the square of the y component. This comes from Pythagorean theorem, basically, because you see if we have our velocity vector here, v, we can break it into, using trig, we can break it into a x component of velocity as well as a y component of velocity. If I were to take these vectors and add them together, maybe take the y component, draw it right here on top at the end of the x component, the head of the x component, I would get the y component of velocity would come up here, and the resultant would be this velocity vector. So you see these are the components of this velocity vector. The magnitude then is simply the sum of the squares, or the square root of the sum of the squares of the components. So the square root of the sum of the squares of the individual components. So vx squared plus vy squared, take the square root of that, you get v. You can see the triangle here and hopefully see the Pythagorean theorem from that. That's where the magnitude of the velocity comes from. The direction can also be given where theta is the angle in standard position measured off the x-axis, measured counterclockwise off the x-axis. And again, using trig, we can see that this theta is going to be the arc tangent of the y component, which would be here, divided by the x component, which is here. That'll give us the angle theta off of the x-axis. So this is how we can break velocity vectors into their x and y components, which is going to be crucial. We have to master this right now, breaking velocities and accelerations into their components. I'm not going to run through this in this video, but take a minute and pause the video and try to work through example 3.1 in the book. We can go over this in class if there are any questions on it. Okay, now accelerations in a plane, we have to consider accelerations because we have two directions here. We have to consider an acceleration to be a change in magnitude, change in the speed, and or a change in direction. If the direction changes, then it is accelerating as well, which we kind of hinted on in chapter 2, right? Like I said on the previous slide, it's going to be easiest to understand the acceleration in a plane if we break the velocity into its components. So we will do that in a moment. But some of the definitions for our average acceleration is the change in the velocity vectors, which was, again, the velocity vectors were a change in the position vectors, but it ends up being pretty much the same equation as what we had in chapter 2. It is, so now we have vectors. It is the second velocity vector minus the first velocity vector divided by the time it takes to get there, or the change in velocity as vectors divided by the change in time. Again, the instantaneous acceleration would be the same exact change in velocity with time, but as the time interval goes to 0. So for sort of a graphical representation of the accelerations in a plane, I said that it would be easiest to break the velocity vectors and as well as the acceleration vectors into their components in order to analyze these. So we don't have to just take one velocity vector minus another velocity vector. There's a whole lot going on because they can be at entirely different angles, as we see here. We have velocity vector v1 right here. This is the instantaneous velocity vector, by the way, so it's tangent to the this curve right here. This is the path, the blue line. And then we have the instantaneous velocity vector v2 right here. Now, if I take the definition of the average acceleration between these two, I've got to take velocity vector 2 minus velocity vector 1, and it's a little bit difficult to do because they're different lengths, they're at different angles. It's hard to do. So we want to break this apart. It'll be much easier to interpret if we break them into the components. So we take velocity vector 1, break it into its component, and I would have a y component that would be this direction. This is v1y, and it would have an x component right here, which is v1x. We do the same thing with velocity 2. We have a v2y here, and we have a v2x here. You can also note that this is like a projectile being launched up. It had a large velocity upwards here, a large vertical velocity, and then the vertical velocity is decreasing here. The x component, it also looks like it might be accelerating because the x component was small here, and the x component is actually getting bigger as it goes along. So there's something pushing it. Anyways, the acceleration, the average acceleration between these two is the change in this velocity divided by the time. We'll just kind of assume the time is 1 second for simplicity here. So we can break this into its components. We don't necessarily have to just subtract the entire vector. We can just subtract the vector components. So in order to get the x direction of the acceleration, I'll take v2x minus v1x. So just subtracting the x components, I can get subtracting the x components of velocity, I can get just the x component of the acceleration, right? So we have here the delta Vx would be V2x minus V1x, which gives us this guy right here. That's this one minus this one gives us this one right here. Doing the same thing in the y direction, we have this vector here, that's V2y, minus this vector here, this is V1y. We subtract them, and we'll get this vector here. This is delta y is equal to V2y minus V1y. So this is our delta Vx, this is our delta Vy, this is essentially our acceleration in x, and this is our acceleration in y. Or we could combine this back together. We broke into components, did the math, so we just had to use a little trig, break into components, then just arithmetic to do the math, and we got these, and now we'll use trig to put it back together just to get delta V. Oops, I clicked the wrong button there and this popped up. Sorry about that. This popped up at the bottom. We have the delta V is this vector right here. Now the average acceleration is simply delta V divided by delta T. So average acceleration in x is just the change in velocity in x divided by the time. The average acceleration in y is the change in velocities of y divided by the time. So this is your average x acceleration, this is your average y acceleration. Again, I can, after we did the arithmetic on it, we can put it back together and we can get a average acceleration vector. So this is our change in velocity vector, this is our average acceleration vector. Put them back over here for a comparison, and you can see that they're actually in the same direction. So the average acceleration has the same direction as the change in velocity, which makes sense because average acceleration is a change in velocity, right? So we have here, and of course the length of this is going to be dictated by the time. If the time here is apparently a little bit less than 1 second, which makes the acceleration vector a little bit longer. Again, we can do the same thing for the directions and magnitude of the average acceleration vector. So we can say theta. If I measure theta from in standard position from the positive x-axis counterclockwise, then theta would be the arctangent of the delta y vector divided by the delta Vy over delta Vx. So the change in y component velocity divided by the change in x component velocity. Or the arctangent of the average acceleration in y divided by average acceleration in x. And again, the magnitude comes from Pythagorean theorem again, where we have the magnitude here represented by the absolute value symbol is the square root of the sum of the squares of the individual components of the acceleration. If we look at the instantaneous acceleration, we would break this apart. And actually, let me, before I get into the instantaneous acceleration, let me just kind of point out that this up here kind of makes sense, right? If I look at how the velocity is changing, well, it was going upwards and slightly to the right, mostly up. Now it's going mostly to the right and not up so much. So it seems that it is moving down a little bit more and to the right a little bit more. So down and to the right, right? It sort of makes sense. The instantaneous acceleration here, you really need to have a point close by if you're going to, in this class, in order to find out quantitatively what these the direction of the instantaneous acceleration is. But you can see that this is the path here is moving up, and then it's starting to slow down and it's starting to move more to the right. So the instantaneous acceleration is something that's down a little bit and something that's right a little bit. So we have our instantaneous component in the x direction of acceleration is here, and the y component of instantaneous acceleration is down here, and we would get our instantaneous acceleration vector looks like this. Again, the magnitude of acceleration instantaneous is same thing from Pythagorean theorem. It's the square root of the sum of the squares of the individual components. And the angle theta they would make in standard position measured off the positive x-axis would be the arctangent of the y component of acceleration divided by the x component of acceleration. So a quick little question, you guys can just look at this and see, does the instantaneous acceleration have the same direction as the instantaneous velocity? Is this a requirement? So we have our instantaneous velocity here, and we have the instantaneous acceleration here. Obviously, they're not in the same direction, so no, we don't necessarily have to have the instantaneous acceleration the same direction as instantaneous velocity. There's actually only a couple special cases, or actually there's two special cases in which it would have the same direction, or actually one special case has the same direction, one special case would be 180 degrees off, and that's if it's just speeding up or slowing down in a straight line. But we'll talk about these special cases more here in a second. So quick little kind of recap quiz. Does a particle in a curved path with constant speed have acceleration? So it's moving at a constant speed. Is it accelerating? It has to be, because it's in a curved path. It's following along some curve. So it has to be accelerating because it is changing direction. So anytime a particle changes direction, it is accelerating. Does a particle in a straight path with constant speed have acceleration? So again, we have constant speed. The only difference here is we have a straight path. Does it? No, it doesn't, because if its direction is not changing, and neither is its speed, then those are the only two things that change acceleration. So no, it's not accelerating. So here we're talking about the cases I was just talking about a second ago, in which we have the acceleration, instantaneous acceleration in the same direction as the instantaneous velocity. If we have that, that's in case A right here. We have our instantaneous velocity v1 right here, and we have some acceleration, which, if we have acceleration is just delta v over delta t. So if we're given an acceleration, we could find delta v, right? So this acceleration gives us a change in velocity, and we could add these two together. So over some time interval, when we add these two together, we would get a new velocity. It has the exact same direction as velocity 1, but it has a longer arrow, so it has a bigger magnitude, it has a larger speed. It has the same direction, but a larger speed. So an acceleration parallel to an object's velocity would change the magnitude of it, but it would not change the direction at all. It would continue moving in a straight path. Alternatively, if I flip this acceleration vector around and have it pointing down here, then this delta v would be pointing the opposite direction, and we would have an anti-parallel acceleration vector. So we'd have an anti-parallel velocity, change in velocity. So that would result in reducing the velocity 1, so we'd get a shorter velocity 2. We'd have a velocity maybe about this long right here. Second case is that, we have one case that it acts parallel or anti-parallel, and we have another one in which it acts perpendicular. So if you imagine yourself driving along and you have a big gust of wind, and the gust of wind maybe just shifts you to the side. It doesn't actually change your speed, it just shifts you a little bit, and you feel it when you're driving along or walking along, or maybe riding a bicycle. It'll shift you over a little bit. So if we have a acceleration that's perpendicular to the velocity vector. Here's our velocity vector v1. We have an acceleration perpendicular to it. It'll obviously cause a change in velocity, which is also perpendicular to it, because what we know from a couple slides ago is that the acceleration vector and the delta change in velocity vector have the same direction, right? So acceleration this direction causes a change in velocity this direction, but has absolutely no magnitude or no change whatsoever on the magnitude. So what happens is that this length is the same as this length, and it changes it some direction. It has the same exact magnitude. It'll have the same speed, but it will have a different direction. So it's a perpendicular acceleration causes a change in direction, but it does not cause a change in speed. This is very important for understanding uniform circular motion, which we'll see later in this chapter, and then we'll get into more in-depth uniform circular motion as we get into chapter 6, 9, 10, etc. So we need to understand that this perpendicular acceleration causes a change in direction, but not a change in magnitude. So, like I just said, we'll be seeing a lot more of this in chapter 6. But here's a quick little question to think about. If a particle is in orbit with a uniform circular motion, so it's staying in a circle, meaning that it's uniform means that it's constant speed, and circular, it's in a circle. Does it have acceleration? So similar to the question we just asked about the car driving and it goes around a curve. It has a constant speed, but if it's going in a circle, that's definitely a curved path. So if it's traveling in a curved path, the direction is changing, so it must be accelerating. So absolutely, it's accelerating. What direction is the acceleration? Now, it's going around in a circle, and it's accelerating, and I know that its change in velocity is the same direction that it's accelerating. We know that from the previous slides. So how is its velocity changing? Its velocity is changing. It tries to go off a path, but it keeps getting sucked back towards the center. So it's actually accelerating, and we'll cover this a little bit more in class, or quite a bit more in class, really. The direction of the acceleration must be towards the center. The particle is trying to go off the path. So we have here, if it's going in circular motion, it's trying to escape here. It has some instantaneous velocity like this, right? Instantaneous velocity is here, but then the next instantaneous velocity is here, and then here, etc. So it's changing over here, like it's changing over a little bit. So it's pointing towards the center, because the particle is constantly sort of being pulled towards the center. So it's inward and it's perpendicular to the velocity, just like we saw in the previous slides. It has to be perpendicular to the velocity, or otherwise the speed would be changing, right? So since the direction is only changing, it's perpendicular to the velocity. And if it's perpendicular, you really only have two choices, outward or inward. And it makes sense that it's inward since it's staying close to the center. If the particle in question is a rock on the end of a string, and this is really getting into chapter 6 here, but this is just a quick preview. If the particle in question is a rock on the end of a string, what would cause the acceleration? So imagine yourself tying a rock to the end of the string and rolling around. You probably would feel a little bit of a pull on your hand, right? So that pull on your hand is transmitted to the rock, and that is what's causing the rock from flying off the path. So this is just little tidbits to think about. We'll get into this a lot heavier into chapter 6, but what's causing the acceleration is the tension in the string. And maybe some of you, if you've seen some physics before, this will actually be related by F equals mass times acceleration, which we don't need quite yet. We won't need this until chapters 4 or 5 and beyond. Projectile motion. So this is, we said we're going to constrain we're actually not constrain, we're going to frame these questions to fit specific types of problems involving the motion of projectiles, things that are launched, right? We call that projectile motion. So the projectile motion is determined by several things. How fast we started off, or the initial velocity that we give it. So here's our initial velocity here. How big is this initial velocity? If this were a football, so this is a football I'm kicking, this is trajectory, means the path that it follows. So this is the path it follows. If I were to make this much smaller initial velocity, then the path or the trajectory might just be something like this. If I were to make it much larger, so our initial velocity vector came out to here, then our path would be much further and it might go off the screen. It's also dictated by gravity. How quickly, you can see that gravity is going to pull it back towards ground, the earth, right? And this actually kind of acts like our acceleration to stay sort of in a circular path. So the gravity or the acceleration downward is going to dictate the projectile motion. If I have less gravity, then there's nothing to pull it down, and it might just rocket off like this. I shouldn't say. If I had no gravity, then there'd be nothing to pull it down, so it would just continue in a straight path all the way up the screen. If I have less velocity, then it would, go do something like that. If I have, or not less velocity, sorry. If I had less gravity, then it would make a larger path like this. If I had more gravity, then it would come down much quicker again. Air resistance also comes into play. So air resistance is going to limit how fast something moves through the air. It's like a frictional resistance, so it slows it down, and that comes into play as well. So things like footballs, baseballs, these are all projectiles. Anything that's launched through the air. You can fire a bullet from a gun, fire something from a cannon. You can drop or throw something off a roof, throw a water balloon. All of these are projectiles. Shoot a basketball, etc. The path is parabolic, which is important. It makes calculations a lot easier. It'll save you guys time on your exams if you understand that the path is parabolic, meaning that we have the high point is right here in the middle. As long as it's going to land at the same height it was launched from, then the high point is right here in the center, and the details of this are almost identical to the details of this, except it'll have a positive y component velocity here, it'll have a negative y component velocity here, but their magnitudes will be the same. So everything is duplicated on one side as it is the other. That's important. And the acceleration due to gravity is negative g everywhere. So it doesn't matter where it is accelerating downwards at a rate of 9.8 meters per second squared. All right, so here is one of probably the harder concepts of projectile motion, maybe one of the harder concepts of this class. It seems really straightforward until you start using the equations, and it tends to stump a lot of students. But the path, or the motion, I should say, of the x and y components are entirely independent of each other. They will have two equations. We'll use the equations of motion for both the x direction as well as the y direction, and they're independent of each other. It doesn't matter. I can drop a ball and it drops straight down here, and the rate at which it falls is exactly the same as the rate at which the yellow ball falls, and it has no dependence whatsoever on the fact that this is also moving to the right some. So this x direction has no play in how fast the y direction moves. They are entirely independent of each other. So you can see that the ball is in the same place vertically every single time. Okay? So the x direction is entirely independent of the y direction. Now, that doesn't mean that we are not going to use them interrelated, because if I'm shooting something up, I'm going to need to use the y direction in order to find out how long it's in the air, so then I can figure out how far it's going to go in the x direction. So I do have to combine them. They are interrelated in the sense that how long it's in the air dictates how far it moves, which makes sense, but the motion themselves are independent of each other. The fact that it has some x component doesn't make it fall any faster or slower. So if I were to drop a ball, or if I were to shoot a ball out horizontally, they will both hit the ground at the same exact time. So sort of maybe a little bit better or different representation of what I just said. We'll use some graphics here. And let's say that I have some projectile, I kick a football, and it moves along this trajectory that is this blue line right here. Now, when I kick it, it has some initial velocity, which I can break into its vertical components, and I can break into it in its horizontal component. And I kick it, and then it moves up, and it's being accelerated downward at a rate of 9.8 meters per second squared, or acceleration is negative because it's downward, and I said that positive is upward, so the acceleration is a negative g. G represents gravity. So it's being accelerated downward. So what happens to my vertical component of velocity is that it gets smaller. It's large here, and then it gets smaller and smaller here until it dwindles down to absolutely nothing right here. There is no more there's no more vertical velocity, no more y component of velocity. It is entirely diminished by the acceleration. But that doesn't mean that it's not accelerating here. This is the point at which the acceleration is sort of wiped out all the initial velocity. And so it continues to accelerate, and we see that now we have a negative velocity down here. At 0.3, the velocity is negative, and it'll continue to become more and more negative as we go along. Okay, so you can see this in the vector. Instead of looking at the components, it is going up, more horizontal, strictly horizontal, and then down, right? It makes sense. It goes up, and it slows as it goes up. It slows down, at least in the y direction, as it goes up, and then it speeds up in the y direction as it goes back down. Now, that's the vertical component, but that's independent of the horizontal component. The horizontal component is an entirely separate thing. And I look at this and I say, all right, we started out with an x component of velocity right here. And I want to know what the x component is going to be here. And unless there's something to change the velocity, unless there's an acceleration in the x direction, the velocity is not going to change. And do we have an acceleration in the x direction? Hopefully you say no, because this acceleration here is strictly in the y direction. There is no x direction. You might say, well, there's air resistance, but this is one of those the fundamental assumptions that we have to make for projectile motion, is that there is no air drag. It's not going to slow it down. Which, unless you're launching something very big or very far, then this isn't a completely unreasonable assumption. But air drag would make life a lot harder, so we won't deal with it yet. So if I start off with an initial component of velocity in the x direction, I actually keep that same magnitude in the same direction. I still have v1x is exactly equal to v2x, or v not x, which is actually equal to v2x, which is also equal to v3x, which is equal to v4x if I had a fourth one over here. You can see on the bottom here, all of these x components of velocity are exactly the same, because there is no acceleration in the x direction. The x component of velocity remains exactly the same. So if I were to ask you a question on a test and I give you a angle right here and a velocity and a magnitude velocity, you can break this into x and y components. And then I can ask you anywhere on here. I can say, oh, right here, what is the x component of velocity? And you're going to tell me it's the exact same as it was here. What's the x component of velocity here? Well, it's the exact same as it was there. What's the x component here? It's the exact same as it was there. It's the same everywhere. So once you found it once, you found it everywhere. As long as we're dealing with the assumptions of projectile motion, we don't have any air friction in there, which we won't. So, okay, little, obviously not really a quiz, but a quiz for you who are taking this video. The initial velocity. How can we denote the initial velocity? We could either give it, and we're talking about in two dimensions here, right? We're talking about motion in a plane. So we can either just say it's some initial velocity and some angle theta, or we could say we can give it in the component. So I can give you a v naught x and a v naught y. So either one of these works, v naught and theta, or v naught x and v naught y. This would explain both x and y components, as well as obviously this one would explain the x and y components. What is the distance the projectile travels depends on what? It's what sort of things dictate projectile motion. You can run back in the video a little bit and see this. It's the initial velocity, the gravity, acceleration due to gravity, and air resistance, which this last one is sort of irrelevant because we're going to neglect it. We're going to say it's not irrelevant, but for all intents and purposes at this point, we're not going to consider this. So really just the initial velocity and gravity. And even this one is going to remain a constant negative 9.8 meters per second squared, or a constant 9.8 meters per second squared downward. So it comes down to the initial velocity. What is the initial vertical acceleration? The initial vertical acceleration would be the acceleration whenever it's starting. So what is that? What is the vertical acceleration everywhere? That'll help you out a little bit maybe. And hopefully you said that the vertical acceleration everywhere is simply downwards 9.8 meters per second squared, or downwards we'll say negative, and 9.8 meters per second squared is g, so it's negative g. What's the vertical acceleration at the top of the path? Well, acceleration is the same everywhere, so that is also negative g. What's the vertical acceleration just before it hits the ground? After it hits the ground, we have an entirely different problem, but what's the vertical acceleration just before it hits the ground? Again, negative g, because the vertical acceleration is constant everywhere. It's always negative g. So next question, if we take air resistance out of it entirely, how does the horizontal velocity change throughout the trajectory, throughout the path the particle moves on? Hopefully after the last slide you say that it doesn't. This is a trick question, and it doesn't. The horizontal velocity does not change whatsoever. What is the vertical velocity at the top of the path? And think back. I pointed out the top of the path, but I said I gave you the vertical velocity. So at the very top of it, its highest point, it's not moving up, nor is it moving down. It is actually, as far as vertically, it's not moving. It's stopped. It's instantaneously stopped. So the vertical velocity at the top of the path is 0. There is no vertical velocity at the very top. And we'll be able to use that fact to find the high points and whatnot. If we neglect air resistance, and a ball lands at the same elevation as it's kicked, just like we had in the previous slide there, how would the initial and final velocities compare? So the entire magnitude, not just the x component or the y component, but the entire final velocity vector versus the initial velocity vector. And I said that everything is parabolic. So as long as we're gonna kick it at the same height at which it lands, the x component doesn't change, and the y component was positive, and then it becomes negative, right? So we have they're going to be negative of each other. So actually this is just the y component. So the y component of the final velocity is negative of the y component of the initial velocity. Okay, so getting into the mathematics behind how to find quantities in projectile motion, we're just going to take the same equations that we used in chapter 2, and we're going to just make a whole new set that's duplicated in the y direction. So we have same equations, it's just in the x and y directions now. So we had this first one, Vx is equal to V naught x plus axt, we do in the y direction as well. So it gives us two equations for x and y relating velocity, acceleration, and time. Same thing here, we have x equals x naught plus V naught xt plus 1/2 axt squared. And we do that again in the y direction. So y equals y naught plus V naught yt plus 1/2 ayt squared. And we'll do that again for this third one. Vx squared equals V naught x squared plus 2ax delta x is Vy squared equals V naught y squared plus 2ay delta y. That's the delta. So if we have no acceleration other than that due to gravity present, then the horizontal distance projectile travels is what? That makes sense to you. Where there's no acceleration other than that due to gravity in this problem. So there's no acceleration in the x direction is another way, is what this is saying. And the horizontal distance would be x is equal to x naught plus V naught xt, right? We've just taken out the acceleration part here, right? Or I can say, since x minus x naught is delta x, we can say delta x is equal to V naught x times time. But V naught x can be given in terms of just V naught and some angle theta, where the x component would be cosine theta. So V naught x is V naught cosine theta and then times time. So delta x is the initial velocity times the cosine of theta, the angle at which it's kicked, as long as the theta is in standard position, and times the time. That would give us the horizontal distance. So if I'm given an initial velocity, I'm given an angle, and I'm given a time, I can find delta x. But what if we aren't given the time? How would we find the time? What if we're just given some V naught and some theta? How would we find the time? So this is where, as I mentioned to you guys in the first day of class, this is where your physics class is going to get different than a math class. You have to change the way that you approach the problem. You have to consider all these concepts that we're learning from the reading and lectures and videos, and then we need to apply the mathematical formulations to the concepts. So how do we find the time that the projectile stays in the air? What sort of things are important to consider? Because that's what we're looking for, right? The time that it stays in the air. We might want to consider whether or not I throw it straight up. Am I throwing it straight up? Am I throwing it straight down? Am I throwing it straight to the side? How fast do I throw it? If it's not horizontal, I'm going to need to know how fast I'm throwing it, the magnitude of the velocity. Is the place it lands the same elevation as where I threw it from? Or did it lose some elevation? Did it gain some elevation? Some other things, we're not really going to talk about this, but some other things we could talk about in physics is there an updraft keeping it in the air? Is there something kind of lifting it up, some wind pushing it up? Does it shoot up and then there's a parachute open up at the top that prevents it from falling back down quickly? Does it go so high that the effect of gravity changes? Do I launch it out of the atmosphere of the Earth and the effect of gravity changes? These are all things I would need to consider. We're not going to consider these three right here, but we will consider these top three. They're going to be very important. So of those things, if we neglect the air resistance, the changes in gravity, all those other things, the parachute opening, etc., and we assume that the landing point is at the same elevation as the starting point, then the equation would get a lot easier. So we consider the equation we saw in chapter 2, just now applied to the y direction. Y equals y naught plus v naught yt plus 1/2 ayt squared. And we let y equal y naught, which is equal to 0. So this is just the starting point is equal to the landing point, which we'll call them both 0. We'll just set our coordinate system so that these are both 0. And then we know that v naught y, the y component of the initial velocity, is initial velocity times the sine of theta, v naught sine theta. And the acceleration of y is equal to negative g. This is something we just assume in projectile motion on Earth, right? If we could be given a different gravity on a different planet. And then we would have y is equal to y naught plus v naught yt plus 1/2 at squared becomes 0 is equal to v naught y, this guy right here, times time minus 1/2 gt squared. So that's just plugging in 0 for y and y naught, v naught sine theta for v naught y, and negative g for ay. So we get this right here, which allows us to find time as long as we know v naught and theta. So of course, we could solve this for y, v naught y, ay, etc. We can solve it for any of these variables, and that's maybe one of the things that can be confusing is because I can give you any one of these variables or any three of these. How many variables we have here? 1, 2, 3, 4, 5 variables. I can give you 4 of the 5, and you could find the 5th, right? Or if you have 2 equations, if we can use this in combination with the x, we could give you 3 of the variables, and you can find the other 2. So there's a lot of other ones we can solve for, and you should practice rearranging these equations and solving for different ones. Try a problem that you solve for one, try to solve it for a different one as well. So as long as we have v naught and theta, we could find t from this, right? Which was all we were looking for on the previous slide, right? So, and we had v naught and theta there as well. So we make some of these simplifying assumptions, actually not a whole lot of assumptions, but just y is equal to y naught. It lands at the same place. If we're given where it starts and where it lands, then this will become a number, which is just as easy to deal with as it being equal to 0. And we can find out how far it goes just by knowing v naught and theta. So some of the key terms here is on page 77 in your book. This is just a summary of some of the key items that we've developed here. So x is equal to v naught cosine theta naught times time. Theta is the arctangent of vy over vx. Y is v naught sine theta times time minus 1/2 gt squared. Vx is v naught cosine theta. Vy is v naught sine theta minus gt. All of these are derived in your book, and we'll go over them a little bit more in class, but this is just a list of some of this key. So this is a good example to work out. Try to work this out before we get into class, and we can go over it some more in class as well. But this is a good example where we have y given to us and we have y not given to us. So this will give us a number. Y minus y naught would be negative 1.5, meaning that it fell 1.5 meters. we're given initial velocity in the x direction, but we're also, because they give us an initial velocity in the x direction of 75 meters per second, the way it's written here, it says this is strictly in the x direction. V naught x is 75 meters per second. So there, nowhere on here does it give us a v naught y. So the y component of velocity is equal to 0. So that's something we have to be able to get out of this. So v naught y is equal to 0. V naught x is 75 meters per second, just as good as being given a velocity and an angle, right? Our angle here would be 0 degrees, and our initial velocity would be 75 meters per second at 0 degrees. And so we have all the things that we needed between the last two equations in order to figure out how far it's going to go. So try to work that problem out before class. I don't have it worked out in this video here, but we'll do it in class. So a little bit more stuff to talk about the horizontal displacement and how it is dictated by the angle in which it's launched, or angle at which it's kicked or fired or whatever angle at which it shoots out from here. And you can see this if you look at the range equation, which is derived in your book, and we'll go over this some in class too. Is it's an example 3.5 on page 81. Work through that example, and they come up with the range equation in there, and that makes it very obvious to see that the maximum distance, the greatest range, the range is the horizontal distance at which it will travel. This is the range here. The greatest range is going to occur at 45 degrees. If I shoot less than 45 degrees, it just doesn't quite get the height here, and doesn't make it the furthest distance. If I shoot too high, then, well, it gets a lot of height and a lot of time up there, has good hang time, but then it just doesn't have that horizontal component of velocity to really get it over there in that time. So the best combination of the two is actually at a 45-degree angle. Will give you the greatest range. It's a kind of in between for the horizontal velocity and the vertical velocity, but mathematically you can see that, like I said, if you work through example 3.5. This is a very good example here, 3.4, which we'll do in class. But you see that after a given horizontal displacement, a projectile is going to have a vertical position. So we can actually, if we know the magnitude of the velocity at which it's launched, and we know the angle at which it's launched at, and we know some distance, maybe the distance from the kicker to the field post, we can work backwards to find the height at that distance, right? We have a relationship that we have two equations that relate the horizontal distance, the angle it's kicked, the initial velocity it's given, as well as the height here. So we can be given any one of these, and actually we can even find for a further distance d2 down here, we can find the second time at which it's going to hit that height, and we can find how high it's going to be down here. So there's a whole lot of things that we can find from combining these two equations. We have, like 10 variables, and we can have any two of those be unknown and still solve these. So very powerful equations. But take a look at this example. We will work through it in class, but try to work it out on your own before we do it, so you're prepared with questions that will make the best of your time in class. Another one that you probably want to look at, example 3.7 here, and we'll do this one in class as well. But one thing I want to point out before you try this is sort of the concept behind it. If you have a guy sitting up here about to drop a pear, and you have another guy down the ground that wants to hit the pear, and he's gonna drop the pear at the same exact time that he launches the arrow. Now, where would you aim? You might say, well, it's gonna fall, so I should aim below. But in reality, if you do that, it's going to shoot a little bit lower. And I should mention too, this is an idealized circumstance in which we have no wind resistance whatsoever. Wind resistance would actually slow this fall, and it would also slow this arrow. So it would have some changes, and we'd have to take into consideration the shape and whatnot. But to simplify this, we assume there is no air resistance, just like we do with all the projectile motion problems. So there's no air resistance whatsoever. They're in a vacuum. So if he drops this, then it's accelerating downwards at a rate of 9.8 meters per second squared. This is the acceleration here is negative g. Now, he launches this arrow, and as soon as he launches this arrow, as soon as he shoots, it's also accelerating downwards at a rate of negative g. So they actually have the same acceleration downwards. So this is going to accelerate down while the arrow is coming over, and the arrow is also going to accelerate down while it's moving over here. The amount they accelerate down is going to be the same time. It's going to be they'll have the same change in their vertical velocity. And so what happens is that the drop, if there was no acceleration, this arrow would go exactly like this. But because there is acceleration due to gravity, the arrow actually moves like this. And the amount that it kind of moves down, this difference right here between where the arrow would have gone and where the arrow actually goes, is the same exact distance that the apple or the pear has dropped. So the interesting thing here is that if you want to shoot in a airless world, if you wanted to shoot the pear out of this hand, you would aim exactly at the pear, and it would hit it down here, but they would be pulled down by gravity, both of them the same amount, and so it would hit here. Interesting concept, good one to understand, important one to understand. But like I said, work through this example, and we will work through it in class as well. Okay, moving on to uniform circular motion. When a particle moves in a circle with a constant speed, that motion is called uniform circular motion. Uniform meaning the speed is the same. Circular just talks about the shape of the motion, right? So in order for this particle to follow a circular path, the velocity must always be changing at the same rate. I forgot a must in there, but the velocity is always changing at the same rate, or must always be changing at the same rate. Or in other words, what is constant? If the velocity is always changing at the same rate, and a change in velocity is acceleration, right? So the acceleration is always at the same rate, so we say the acceleration is constant. Okay, so in order for the particle to follow a circular path, the acceleration is constant. Now, what direction is this acceleration? We talked about this a little bit ago. The direction of the acceleration must be perpendicular to the velocity, right? And we said it can be either in or out, and if it's staying in a circular path, it must be inward, toward the center. So that's the direction of the acceleration here. So the acceleration is always towards the center, or we say that it is center seeking if we have uniform circular motion, or we call this centripetal acceleration or meaning the center seeking. So the acceleration towards the center, the perpendicular acceleration towards the center is centripetal acceleration. This means the velocity vector will not change in magnitude, it will only change in direction if the acceleration is centripetal. A couple of figures we have just to illustrate this. In the first figure down here, we have a car that's rounding a curve. Actually, we have a car that's rounding a curve in all of these pictures with different acceleration vectors. In the first case, we have an acceleration vector like this. Well, and we have our velocity vector is the same in all cases as well, right? So the velocity vector is this. acceleration vector is this. If I break the acceleration into not really x and y components, but I break it into a parallel component and a perpendicular component, because you can tell a lot more about what's going to happen to the velocity if we have it in parallel and perpendicular components, right? So the parallel component is going to increase the speed, whereas the perpendicular component is going to cause it to turn, in the direction of the perpendicular acceleration. So it's going to speed up and it's going to turn kind of towards the right, down and towards the right. So we get it following this path right here. It accelerates like that. Next figure over here, we have an acceleration vector that's down a little bit more, right? We break into its parallel and perpendicular components. Parallel component is going to cause it to slow down because it's the opposite direction of its velocity vector. So it's going to cause it to slow down, and it's also going to end up turning to the right. So it's slowing and turning to the right, whereas this one was speeding up and turning to the right. If I have, in the third one, we have a acceleration vector is only perpendicular. There is no parallel component of it. So this one is going to have a uniform speed. Speed is not going to change at all, and only the direction is going to change. So it's neither speeding up nor slowing down. Only the direction is changing. So in all these cases, we have acceleration, but different forms of acceleration. This one's the speed is not changing, but the direction is. This one, it's slowing, so the speed is changing as well as direction. And this one, its speed is changing because it's speeding up, and direction is changing as well. So we can solve this also for the velocity in terms of the instantaneous velocity, in terms of the radial or centripetal acceleration. Sometimes we'll write ARAD. This is radial acceleration, which is the same thing as centripetal acceleration. So I may on the board either write a radial or a C for a centripetal. They're the same thing. Radial acceleration and centripetal are the exact same thing. From your book, this is on page 86 in your book, figure 3.24. I'll kind of briefly run over the derivation of it, but really the most important thing is the result we get from this. But if we have two velocities, we have some in figure A up here, or part A of the figure. We have something's fallen this path right here. It has an instantaneous velocity v1 here, instantaneous velocity v2 right there, and it's traveled some distance along this path, delta s. I can extract putting this v2 over here, the tail of v2 on the tail of v1. I'll create this triangle right here, and we know the difference between v2 and v1 is delta v. We'll get right here. These two triangles are similar. This triangle right here is similar to this triangle right here, and so their ratios are also proportional. They're equivalent proportions. So we can say that delta v over v1 is equal to delta s over r. That's how we get they're similar triangles. So these ratios are the same. So we say that the magnitude of delta v, running through the algebra, and maybe it's best to just open up your book. I don't have it in the slides here, but maybe it's best to open up your book and follow along here. This is on page 86. You get delta v, doing the algebra, you get delta v here is going to be equal to v1 over r times delta s, just doing the algebra, because delta s over r is equal to delta v over v1. Doing the algebra, you get that. I'll leave the rest of that for you guys to follow, and we'll do a little bit on the board if there's questions. But running through and solving that for the average acceleration, saying that average acceleration is change in velocity with time. So change in velocity with time would be delta s over delta t. We run through the algebra there. We end up with the result where a radial, the radial acceleration is velocity squared divided by the radius. So it's the instantaneous velocity v, so at a point here, v squared divided by r, the radius of the path. So even if it's on a circular path, even for an instant, and then just the radius of that circle that it's on for an instant is this r. So this is the radial acceleration or the centripetal acceleration. Which are exactly the same thing. So like I said, I might say a radial or a c when doing problems in class on the board. Some really important things about uniform circular motion. Do not think of an object as accelerating outward from the circular path. I know that if you remember when we had that example where we had a rock on the end of a string, and I said, well, it feels like something's pulling out, but really what's going on is you're pulling in. There must be something to pull the object in to stay on that path. It's accelerating inward, not outward. The idea of centrifugal acceleration or centrifugal force is wrong. It's centripetal acceleration. So we have, or centripetal forces, we'll get into later on, but do not think of it as accelerating outward from the path. Instead, try to think of radial acceleration or centripetal acceleration as a requirement and that the object must absolutely follow in order to stay on a circular path. It's not going to be on a circle. It's not going to follow a circular path unless it is accelerating inwards at a rate of v squared over r. At this rate right here, for this radial acceleration, has to be the rate at which it's accelerating towards the center has to be velocity squared over r. And this, because velocity is squared, this is actually just the speed squared. So you can just be given the speed and still find the radial acceleration. So it must be accelerating inwards at a rate of v squared over r. Otherwise, it's not following a circular path. Don't think that the radial acceleration is caused by the particle. Think that the particle's path is caused by the acceleration. That's a very important thing to understand. So in other words, for an object to stay on a circular path, it must accelerate inwardly at a rate equal to the square of the speed divided by the radius. So like I said, this is speed squared because direction isn't there anymore if we square the velocity. There we go, back to it. If we have a velocity, either a constant velocity or an instantaneous velocity of 45 meters per second, and we have a radial acceleration of 8.9 meters per second squared, then we can find the radius, because we know radial acceleration is velocity squared divided by r. So 8.9 is equal to 45 squared over r. So r is equal to 45 squared divided by 8.9, whatever that works out to be. Let me do this one quickly here. Another one that we can do really quickly, if we have, we're looking for acceleration, we're given a radius, and we're given not a velocity, but we're given a time here. This is actually, t is a period. It is a period of 4 seconds. Now, t represents as the period, so it's the time it takes for one revolution. So this capital T all throughout the course will represent the time it takes for one revolution. So the time it takes for this to go around like this, one revolution would be going all the way around, it takes 4 seconds. And every 4 seconds it goes around and 1 revolution. So I can get the velocity by knowing the time it takes to go around, because I know the distance it goes already, because the distance is just the circumference of the circle. So the circumference of a circle is 2 pi r. R is 5, so we have the circumference is 10 pi. The distance it travels divided by the time would be its velocity. So 10 pi is our distance. The time it takes to go that distance is 4 seconds. So we're left with 10 divided by 4, or 10 pi divided by 4. So we have 2.5 pi meters per second is our velocity here. And we have a velocity, we have a radius. We can find our inward acceleration because I know it's staying on this path. So it's a radial acceleration. So that is equal to velocity squared divided by the radius. So work that problem out as well, and we'll touch base on in class too. So again, like we did in chapter 2, give you some example problems here. I'm not going to work them out here, but we will work them out in class. But I want to kind of show you how to set them up. So we have this problem here. I'll give you a minute to read it, or you pause it and then read it. But I want to help you to extract the information that we need here. What we should do is we should say, what are we given? Well, we're given the height of this building, and it is 15 meters. We're given an initial velocity of 30 meters per second, and we're given an angle theta above the horizontal of 33 degrees. We're supposed to find the maximum height above the roof that it'll travel. So this is y max. The magnitude of the velocity just before it hits the ground, or v, absolute v, this is the magnitude of the velocity, and the horizontal distance the rock travels, or x. The important assumptions that we need to make are free fall conditions. Right, so we have air resistance, rotation of Earth, and proximity to Earth are all negligible, and that's this is the same assumptions that we made in chapter 2. We're still doing them because we need to apply chapter 2 concepts to chapter 3 as well, and also that the horizontal component of velocity is constant, and it's so if the horizontal component of velocity is constant, this is another way of saying there is no horizontal acceleration, which is another assumption of projectile motion. Together, these all make the assumptions, the general assumptions of projectile motion. So when we're doing projectile motion problems, we need to make all of these assumptions. So we just basically say, and there's a g is constant, right? So g is constant, and there's no air resistance, and there's no horizontal acceleration. We'll work it out, and hopefully you worked it out before looking at the answers, but here are the answers. So another problem here. I'll help you guys break it down into what we're given, what we need to find, and you can try working it on your own, and then we'll work on it in class. So give this a pause and then read it, and then we'll move on. So we're given 3 revolutions per second. We're given a radius of 7 centimeters, which they were asking for an answer in meters per second squared. So I'm going to go ahead and convert this 7 centimeters to meters. It's a good habit to do just right away when you're given some information. If you're given something in centimeters and they're looking for something in meters, go ahead and convert it right away, right up here when you're given information. What are we looking to find? Well, they want us to find the radial acceleration, a radial, also known as the centripetal acceleration. They want us to find it in both meters per second squared and in G's. So when we're solving this, it's important, we find it in meters per second squared, and then 1G is 9.8 meters per second squared. So if I get an answer of 9.8 meters per second squared, I would say, oh, that's 1G. That's an acceleration of 1G. If I get an answer of 19.6 meters per second squared, then I would say, well, that's 2 G's then, because 19.6 divided by 9.8 is 2. If I were given, if I got an answer of 29.4 meters per second squared, I'd say, well, how many G's is that? Then that is 3 G's, because 29.4 divided by 9.8 is 3 G's, right? Let's say I was given something like 65. I get 65 meters per second squared. How many G's is that? Well, I would simply say 65 divided by 9.8 gives us about 6.6 G's. So we're just saying that, 1 G is 9.8 meters per second squared. Sometimes it's convenient to give our answers in terms of G's, because that helps us to relate our weight and forces, which we haven't got into yet, but get familiar with expressing acceleration in terms of G's. Assumptions, we're not really making any assumptions. We could have assumed that there was no air resistance, but they told us that it was a constant 3 revolutions per second. So they told us it was constant. Either tells us that something else is pushing it along the way, or that there is no air resistance. So we didn't actually really need to make any assumptions here, but maybe under assumptions you can say what equations you're going to use. Maybe you put A radial equals B squared over R and the assumptions. So your solution is here. You end up with 25 meters per second squared, which is about 2.5 G's with a little bit of rounding. I think exactly it would end up being 2.55 meters per second squared. So maybe I should have rounded that to 2.6 G's, but yeah. So